NumPy and PyPlot. And following that, we first import the image into the img variable, just a name for this variable given, using the cv2.imread function. We specify the name of the image file, and also we specify how we want to read that image. So given that this image which we are currently using, the Lena grayscale image, this is indeed a grayscale image. So we would want to read it as a grayscale image, obviously, and this would mean that there would be only one channel in this image. So unlike the RGB images, color images, where we have multiple channels, 3 channels for the red, green, and blue color values. So here we would have only one given channel. So okay, so the import is done, as you can see. We just, for the sake of
Sir, hello.
Yes, please.
So what is CV2?
CV2 is actually this is you in the tutorials, in the original like the online tutorials, you would see that this is named as CV, but the current iteration of the OpenCV library is to the best of my knowledge, I think it is CV2. So this is the updated version. If you would want to use it with the latest Python packages, CV2 would be required to be imported into the library, into the project. Yeah. So so after you import the image, you could do one of 2 things to view the image. So you could either open a separate window, which is this one. This is basically a separate window to show the image, and it just waits. The program just waits for you to either close the image or maximize or minimize it.
Sir,
yeah.
Sir, here the image is actually grayscale, or we are importing it as grayscale?
No, the image is actually grayscale. And since we want to, since we are importing a grayscale image, we would like to just explicitly specify that we are just reading it as a grayscale image, as a single channel grayscale image. So just for the sake of just for the sake of completion, just to keep things clear here.
Okay, sir.
Yeah. So of course you can see it as the you can display. Yes, please go ahead.
Sir, if the image was colored and if you use this, if you read this like a grayscale image, will it cause an error or will it take only one channel?
Okay, so let us just run that experiment. So here you can see there is the colored version of the image also, and we can accordingly change this. So if we do that, and if we rerun this part, you can see it doesn't give any error so far. Let us display the image, and you can see that it is again reading it as a grayscale image. So what you can say is that this part is just to explicitly specify that we are treating the grayscale image as a grayscale image. You could obviously import the color image as a grayscale image. That would reduce to the same thing, the same problem. You would still have one channel, and it is basically the same thing. We are just doing it like we're just stating the way we are reading the image explicitly. So yeah, there is apparently no problem so far if you want to read a color image as a grayscale image.
But when we read a grayscale image,
yeah,
sometimes it happens that it is actually read as a color image, but
yeah,
the color is actually gray.
Yeah, that you see, that would happen. That would depend on the specifics of the image. Now, if you read an image as a color image, then what you are doing is then you are not staying true to the task you have, the image processing task that you have at hand. Because if you consider any image processing task where you are feeding grayscale images and you are treating it as you are reading it as a color image, that I think would not be. That does not. It doesn't mean anything significant. It's not a very scientific way of approaching the experiment. So if it is best to clearly specify at the beginning of the importing operation how you are importing the image, whether you are wanting to read it as a color image, what is the image file that you are importing. It is better to know what images you are dealing with prior to an experiment, and how you are wanting to import it into the project that you are about to execute. So these things should be clear. The details of the image, what images you're dealing with, and how you are wanting to deal with that image. So these two things should be clear. So yeah, so I hope that clarifies your question. Yeah, to get back to our original tasks. So after the displaying of the image, we can also plot it as a 2D plot using the PyPlot libraries. So we can see it has a 256 plus 256 dimension. And currently, I am not using this cv.im write, because we are not actually writing any new thing to any writing any new image. We have not really done any operations. So let us jump into. We'll be dealing with the writing operations later on in this project. But let us first jump into how we find the histogram. So when it comes to calculating the histogram, what we are actually getting in a histogram for any image is basically the account of how many times a pixel or a pixel value is occurring within that image. So since we are dealing with a grayscale image here, you would know that since our color encoding scheme is RGB by default, and since we're dealing with a grayscale image, you would know that the luminosity values would range from 0 to 256. 0 standing for absolute black and 256 for absolute white. So suppose you would want to plot how many times an image with, say, brightness value 150, how many times that pixel value occurs. So this histogram would give you a plot. This would give you a count of how many times that pixel value occurs. And this basically, okay, so let us just first run through the basic code. So you store the histogram into this variable using the cv2.calculate.
Sir,
Yeah,
can you show the previous cells once? I have a doubt.
Yeah, sure. You mean these ones?
Yes, sir. So, sir,
Yeah.
here we were importing it as a grayscale image, but the image you showed and the image which is printed
I
is
know.
different.
Yeah, this is you don't need to be worried about this part. I will get back to you with the specifics of why this is printed as a green tinted image, but just rest assured that this is actually the grayscale image. It is just a feature of just an aspect of the plotting mechanism due to which it is shown as a green tinted image. But this is not a green tinted image. It is the same image. It is the same image which has been plotted like so. I mean, it is the same grayscale image which has been plotted as a 2D plot. You need not be bothered about the green tint that you are seeing here. It is not a separate image. It is not something to be worried about. So I mean, you can see it here, right?
Sir, you can use CMap
Yes,
equal
sir,
to gray. It will change to gray.
Yeah. I have not. I have actually not included that feature. So yeah, so that is why it is. That is why it is being displayed as a green tinted image. So yeah. So you need not worry about that for the time being. Let us now move into the So as we were talking about the histogram, so it just gives you a count of the pixel values. I mean, how many times a given pixel value is occurring in the image. Now, as we were saying that we stored the histogram into this variable. We use the calc hist function. We can give the following inputs to this function: the image, obviously, the img variable. This 0 specifies actually that we are calculating the histogram for only one channel, and the none option is basically we are not giving any specific masking features. We are not really applying any masks to the histograms. We are not really saying that, okay, do not consider these portions of the image or anything like that. And this 256 specifies that we are actually calculating the histogram for 256 bins. So 256 bins would mean that we are actually considering each and every pixel value. So basically one bin would correspond to one pixel value, and 0 to 256 would be the, like the ranges of that the pixel values can take. So we can run this bit of code, and correspondingly by plotting the single channel histogram values, we can see that we get something like this. It's the same thing, but now one thing to note from this thing is, although the spatial information is not really retained in this histogram, you cannot really tell where an object is. Directly it is not clearly apparent, but you can actually make some judgments about the exposure information, about the exposure of the image, exposure quality of the image. Now, if you see that there is this peak at about 50, where it is not really a bright part of the image. It is not really that dark, but it is not really that bright. So this peak could correspond to this peak would correspond to this part of the image. If you see the original image, this bit of decoration on the headgear, or the hair, or such parts which are not really well lit, or something like that, which is not really well exposed. And again, you see these peaks over here toward the right. As you move towards the right, you see these peaks, which could correspond to the areas which are well exposed or brightly lit. So this gives you an idea about how the image is exposed, how the image whether the image is overexposed. So if you had an overexposed image, most of these you would have more counts towards the rightmost part of the image. So values close to 56 to 50 to 55, it would be a skewed histogram towards the right, whereas an underexposed image would be skewed towards the left. So that gives you an idea about the brightness, the luminosity quality of the image. And just as you can do it for a single channel, you could also do it for for a color channel. Yes, does anyone want to speak?
Sir, can you shift one cell above?
Yeah, sure.
So here, histar is an array or a histogram object, because it has been passed in plt.plot. That's why I'm a little confused.
This is basically, I believe this would be somewhat of an array. So I guess this is, if we can print this, if we can just print this, we would see that this is basically something of a two-dimensional yeah. So that is what it is, and we are basically passing this into the plot function, and which is being plotted as a two-dimensional plot. So it is just containing, it's just a container of numbers, just values, two-dimensional values. And yeah, so that is for a single channel, for a grayscale image, and and you could do the same thing for color image as well. So it is basically you would just need to iterate over the three channels. You could break down the colors like an enumeration, like blue, green, and red, and just iterating through the colors. You could treat each and every channel like you did for the single channel case. And here, instead of passing 0, you would pass the channel number. So 0, 1, and 2 would correspond to so blue, green, and red. And again, again for again you would have to consider 256 bins and 0 to 256 pixel values, and it's the same bit of code. Yeah, does anyone want to speak?
Sir, what do you mean by channel? I'm not getting it.
Channel is basically what you mean. Channel is basically what you mean when you say that you have a color image. So in an RGB system, you can basically break your color image into three. So in simple terms, you could say that a color image in an RGB system is a combination of three images, each of which so you have three images: a red image, a green image, and the blue image. If you just break it into very simple terms, so a color image can be broken down into these three constituent images, and each image would have information about that particular color. So the red image or the red channel would have information about how much the red color is being how much the red color is figuring at a particular pixel. Correspondingly, the green channel would have how much how much the green is varying at a particular pixel, and so likewise for the blue channel. So that is what you mean when you say that you have three channels or three colors or like that in a 3-channel RGB system. That's what you mean. So you can that is what we see here. That is what we see here when we break down the channels individually. We are basically breaking down the image into three constituent images, and we are plotting the histogram corresponding to those three images. So this blue plot would be for the blue channel or the blue image, quote unquote. The green channel likewise, and the red channel also for the red quote unquote constituent image. So it's basically the same concept that you saw for the monochromatic, the grayscale image. We're just doing it iteratively for each of the three channels. It's the same thing. It is just showing the color information, the luminosity or the like say the brightness information of the or to put it in a better way, the intensity of the color I mean of each of the channels in each of the channels. So you could see that the blue values peak at these values, these bins, and correspondingly you have the red values which peak towards the right. So you have a lot of intensity over lot of intensity here. There are several pixels in which the red channel is dominant in this region. So that is how you break down the color image. Okay.
What's in the y-axis? Can you explain me?
Yeah, the y-axis is basically the count. So this is basically giving you a count of how many times a given pixel value is occurring. So if you just for the simplicity of explanation, if you just go back to this image, you would see what this says is that how many times say a pixel with value 50, say a pixel with brightness value 50 is occurring. So this will be at somewhere around 300. Correspondingly, how many times a pixel with brightness value 150 is occurring? So this is somewhere around 700. So that is what it is saying. And for the color image, it is telling that how many times a pixel with in which the so if you just take the blue channel, how many times a pixel where the the intensity of the blue channel is at around, say, somewhere between 800 to 900 is occurring. So it is this same argument is being extended to the color image. It just shows the intensity of the intensity for each of the channels. That's what is happening.
So that x-axis, is it fixed for every image, or we can change the intensity number of intensity variables? Like, is it 256 every time, or?
See, 256 is something which is considered for the RGB system. Now, if you have other systems, I would not say I have worked with other systems, so you probably have heard of like subtractive systems like CMYK and other things. I have not personally worked with that, but the basic image processing tasks, you basically can break it down to 256. You can consider 256 pixel intensity values. So yeah, so okay, and this is again following the histogram operations. We have some transformations and shuffle operations here. So you could, I guess, carry out a transpose operation like this. And what that does is just just transposes your image. So
Sir,
yeah.
so in the grayscale image, because like there aren't multiple colors, so we use just a single channel. Sir, but in that the color was red.
No. This is see that this is just a display convention.
Okay,
You
so it's
could,
not the it does
yeah,
not
yeah,
correlate with the fact that there's a, okay.
no. This is just a display convention. You could have it as blue, green. I mean, Python offers several plot colors. So this is not. This is just color equal to red. You have just plotted it as a red curve. That's it. Yeah. So you could transpose the image as we saw here, and transposing the image actually comes in handy when you would want to. There are several other transformation operations, so I could just tell you it right over here. So transforming these images like so, like flipping the image or rotating the image. These things come in handy when you would want to augment your data set, or say you want to increase the size of your data set. So suppose you have suppose you are training a neural network model or any machine learning model, say on faces, for instance, since we're dealing with a facial image. So you could say that if you give facial images of a particular type where the eyes are always on top and the nose and lips are somewhere towards the lower half of the image, you could pose an argument like, what if the neural network is just getting biased towards detecting objects towards the top of the image as say eyes, and objects towards the bottom of the image as nose and lips. So it is not really learning the nature of those objects, rather it is just looking at the relative position of the objects and just telling that those are the eyes, and since those things are at the bottom, that is the lips, and that is the lip, and that is the nose. So in order to remove that sort of biased that biased way of learning, you could sort of throw it a curveball of sorts. You could augment your data set by throwing the same images, but say it is rotated by a certain degree, it is flipped, it is turned upside down. So we will look into such operations as we move into as we move further into this project, this little tutorial. And yeah, so that was one transposing operation, and then we have the shuffling operations of pixels, which basically, okay, so this is basically just I just printed it. Oh, sorry, there was a naming problem. Yeah, this is just a just a matrix wise representation of the image. It's same thing. Yeah, so what I would want you to see is what you would see when you shuffled the image across a particular axis. So what this function does is it basically shuffles the pixels along the horizontal axis, and also doing things like this, like corrupting the image, also serves a purpose. You might have heard of certain work that was done some few years prior some 4 or 5 years back, which dealt with the fact that neural networks can actually neural networks, which you would get to know about further into the course, that neural networks can actually learn these noisy patterns, and they have the capability to actually classify them as certain objects. So it was seen that although it would take more time to learn noisy patterns, it can actually fit to these noisy data. It can actually fit to absolute noise. It depends on the actual architecture, the nitty-gritties of the model, but it can actually do that. So this can be an interesting experiment if you can corrupt your data set to some extent by providing these images which are just random noises or just shuffled pixels. You can actually see how the whether the network can actually fit to these data points, these images. So yeah, that is one interesting experiment. And then you have then again you have some flipping operations. So if I can just re-import the image, I'll just go back and re-import my image over here just to ensure that we work with the original image. And we come down here to just see how you can flip the image. So you have these 3 possible options, 0, 1, and -1, to flip across different axes. So I'm just going to use the -1 option, and yeah, so basically just it actually does 2 things, I guess. If I am right, yeah, it flips it across the horizontal direction and as well as the vertical direction. So once again, it is basically you could use this again as a means to augment your data set, and to include images which are just reflections of each other, or just just flipped images or rotated images. And resizing images is also a common enough operation. So you could again do a cv2.resize where you feed the original image and you provide the resized dimensions. So this is basically what we are saying is we will convert the width to 4 times the original width and the height to 4 times the original height. So basically image.shape0 represents the like the row and like the width and the height. So we are taking those 2 variables, we are just multiplying them by 4, and to calculate the values of the intermediate pixels, like since we are dealing with a resized image, we would need more pixels to represent that image. We are just using the standard linear interpolation. We have OpenCV does provide additional interpolation options like cubic interpolations and other such options, but just for the sake of the demonstration, we are dealing with linear interpolation. And if you plot the image once again, although you cannot see the increased size, but you can see that the graduations have changed. So this is now 1024 plus 1024, basically 4 times the original image size. Okay. So those were more or less straightforward. And again, now we get into the transformations, the affine transformations that I was referring to earlier. So in these cases, basically you would need to provide what is, we may have studied about this in the graphics course if you have taken. Yeah.
Sir, am I audible?
Yeah, sure, go ahead.
Like, sorry, sir, I have a doubt. Can you go back to the place where you changed it to 1024 times?
Yeah, sure. Yeah, here.
Sir, so how are all those points contacted? Like,
how are all those points contacted?
Like, sorry, calculated. Like,
they are calculated using the linear interpolation, as I mentioned here, right? So you have to.
Isn't it just zooming the image then? Won't it make the quality bad? Like,
it will lead to, obviously it will lead to a loss in quality, but see, once again, at this moment I am unable to think of a good enough example, but just for the sake of if you would okay, so I get your point, but I just wanted to show you this thing that you could do. by just expanding how to expand the image, just zoom into the image. This is let us for the time being just consider this as a basic operation, and I will get back to you if I can find a good enough example. I will let you know on the general channel or through the messaging.
Sir, but some algorithms do exist, right, which can increase the quality of image?
Yeah, there are operations, there are algorithms, but for the time being, we are just treating this as a basic, just a very preliminary resizing operation.
Yes,
so
sir.
Yeah, so that's it. I mean, you may or may not need to use this as a operation when you deal with complicated image processing problems, but just for the sake of mentioning, you might need to know the structure of the code or the options that are available for interpolation when we are expanding an image. So yeah, so just for the sake of the demonstration, we are presenting this particular resizing option. Okay.
Okay, sir.
Okay, so yeah, and I will get back to you if I can find a good use case for this particular for this particular tool. Okay, so okay, getting back to affine transformations. Basically, in affine transformations, if you start with a very basic translation operation, so you would need to specify a transformation matrix. So a transformation matrix is basically something which tells you what is the nature of the transformation that you are trying to carry out. So here we are saying by this M, this is the transformation matrix which we are specifying, and this says that you would basically shifting the image to the right by 100 pixels and to the downwards by 100 pixels. We see the result plotted here. So to use this transformation matrix, we basically preceding that statement is this statement. So here we actually.
Can you please repeat the previous part?
The transformation matrix part.
Yes, sir.
Yeah, so the transformation matrix here, what we are specifying is that we are just wanting to translate the image, just move the image along a horizontal or a vertical direction. So we are doing that by just specifying here. See, as you can see, this is a 2 rows 3 column matrix. So the first row is basically saying that okay, you take the image and you move it to the right by 100 pixels, and then again you can move it downwards by 100 pixels. So that is basically what is happening, a horizontal and a vertical translation by 100 pixels along each axis.
So what does the 1 and 0 signify in this?
So the 1 and 0 signifies it is basically saying, it is basically treating each individual axis. So this is basically along one axis, this is basically along the other axis. So that is why you have the other element as 0. So this is basically the horizontal, and this is basically the vertical axis. So if you can visit the very basics of affine transformations, the mathematical operations of affine transformations, you would see that is how the transformation matrix for translation is defined. So you basically provide the the axis along which you want to translate and the amount by which you want to translate. So this is how you're representing that transformation matrix. So this follows directly from the theory of affine transformation, the translation part. And
if we type 1 1, then will it transform along the axis of along y equals to x?
Okay, so yeah, so let us just do that. Let us just
Sir, what are the 3 parameters for like 3 columns?
3 columns?
Yes.
So these are this is the amount by which you are translating. Okay, this is the you're moving to the right or you're moving downwards by 100 pixels, and these basically represent the x and the y values. So if you as the person before you just mentioned, if you do this just for the sake of experimentation, if you see what happens. So this is what happens. So you basically you know, so you basically move the image out of the frame, and this is not really what you're wanting to do. You are wanting to move the image, you're wanting to move the image in the individual axis by 100 pixels each. So 100 pixels along the horizontal and the vertical directions. So if you revert back to the original operations, that is what we intended to do. So this is actually the transformation matrix which follows from the affine transformation for translation. So yes.
Sir, 100 is the value for which we are moving right
Yeah,
and downwards.
right,
But
right.
10 and 01, I did not understand those.
Okay, so yeah, I'll just show you then the I'll just show you the affine transformation. I did have the materials, but yeah. So this is how it is defined. If you see, so if you ignore this axis, this one, you would see that the tx and ty, that is basically the displacement. So this is this specifies the displacement along the x-axis and displacement along the y-axis. And 1001, this is basically, so 1001 is basically, see, you are actually, this matrix you are actually multiplying with the original image, the locations of the pixels, the individual locations of the pixels. And you would want to, in order to carry out this transformation, this is where matrix multiplication and some multiplication operations and addition comes in. So if you carry out the operations explicitly, if you work it out by hand, this is what you would get, that in order to shift the x pixels, the pixels along the horizontal direction by 100 pixels and the vertical along the vertical direction downwards by 100 pixels, you would need to frame the matrix in such a way that this particular column addresses the x direction and this particular column addresses the y direction. This is just the the intricacy of the matrix itself. This is how you design the matrix. If you go into the detailed theory of the affine transformation, this you would see that by the derivation, by by just working out derivation, you would get the transformation matrix, which can be written like this. And you could go into the derivation, or you could you could just know that this is the structure, and you could work with this, and you could build upon this. But I would suggest you go into just revisit the the mathematics of the transformation. It's not really that complicated, but I guess the basic idea, the basic impression should be clear.
Sir?
Yes, sir.
Yeah. So here, what does it mean to translate? Like, what happens behind? So, like, will it increase the intensity accordingly for those pixel points after 100? Like, how does it?
No. It is not increasing the intensity. It is just changing. It is just saying that that a pixel which had this. So if you look at the original image, so this value would now be moved by this amount. So this value will move by 100 pixel downwards. Correspondingly, the same would happen for all of the image pixels. Now you are seeing this as seeing only a portion of this entire translation. You're not seeing the entire translated image, because we are just viewing the 256 cross 256 panel within which this transformation is taking place. But you're just what you are just saying is that a pixel here will hold the value of the pixel which was originally here. Correspondingly, again, and the same operation would be carried out for all the pixels in the image. That is how you would say that the pixel has moved in this manner. You're just shifting the values of the pixels. That is what you are doing, and it has nothing to do with changing the intensities. That is not, I would say, a very accurate description. But
So like what I meant was updating,
yeah, you're just updating the values. You're just saying that, okay, the value at here should be equal to the value which was upwards by diagonally here. That's it. You're just updating. You're just moving, quote unquote. You're just moving it.
Sir, is the surrounding region always violet after the translation?
Yeah, that is again, we are going into the nitty-gritties of the plot, as one of you just pointed out. If you just change the CMap to the color encoding to gray, then you could see it as a black thing. I'm just displaying it as with the default options. This would be black. I mean, see, once again, do not get bogged down by the the display. I apologize if it is throwing some of you off focus, but this is basically the grayscale image, and this part is basically, it does not have any information. The image has basically moved by 100 pixels to the right and by 100 pixels in the downward direction. That is all that has happened. It has just moved. The pixel values, if you consider the question asked by the person before you, the pixel values have just been updated spatially, like so. That is all that has happened. You did not bother about this patch here. It has just moved. That is all.
Okay, sir.
Yeah. So just as you can do translation, you could also do a reflection as an affine transformation. So when you are doing a reflection, what you need is a relation between 3 points, at least 3 points in the image. So you take any 3 points. So here we take the point 0, 0, which is this point, the point which is basically, so this point, the second point is basically this end, if you can see my pointer, and this point is basically the this bottommost point to the left. So what this is saying is the output points, if you see, so this point is now corresponding to this point. So 0, 0 is now moving here. So this is moving all the way here. You can see it at the output. It is just flipped, and correspondingly, again, I mean, these two columns you can understand. If this has shifted to this, then obviously this will shift to this conversely. This is just the same argument. And again, you can see this one. The bottom point, the lowermost point to the left, the lowermost pixel to the left has now shifted to here. So basically, it is nothing but a reflection. It is nothing but a reflection along the y-axis. So that is how we are representing it as an affine transformation, by specifying the relationship between 3 points at the input and output. So we are specifying the affine transformation, as you see here. We stored that as a affine transform matrix. So that is what the get affine transform function does. It basically gives you the transformation matrix. You don't have to calculate it by hand. You don't have to remember this form. You just need to provide it the input points and the transformed output points. And it just calculates the transformation matrix and stores it in M. And then again, you can feed the transformation matrix M into the warp affine function, just as we did here. It's the same function. And again, the rows and the column values just as before. And that gives us the modified image. We're just then plotting it as a reflected image. So that is what you're doing. You're unlike the previous transformation where you actually explicitly stated the translation matrix, the matrix for the translation. Here you are not really specifying. You are just saying that this is the relation between 3 points, at least 3 points, at the input and output, and you're just is feeding these input points and output points to the affine transform function. The function is giving you the transformation matrix, which in turn you are feeding it into the warp affine function, and that as a result is giving you the transformed image. So again, you could play around some more with the affine transform functions. So you could once again specify the different set of relations between these 3 points. So here, as you can see, the point towards the extreme top left is shifted downwards by 100 pixels. So this is what it means. So 0, 0 is shifted to 0, 100. And but if you see one thing, this point, the top rightmost point is where it is, and also the bottom leftmost point is where it is. So this would be interpreted as a shearing operation, if you call it that, a shearing operation along the vertical direction. Okay, so once again, you don't need to compute the affine, the transformation matrix. You can just get the transformation matrix by get affine transform, and again feed it into the warp affine function and get your transformed image. So all these things, again, I mean, to reiterate the earlier point, you could always use these things to to expand your data set, to to test whether your model can pick out features like facial features within these transformed images, these shared images, or reflected images. Whether again, you can also rotate the image. So for rotation, to get the matrix corresponding to the rotation operation, you could use the get rotation matrix 2D, and this takes actually these 3 arguments. So this first collection of values, columns by 2, rows by 2, specifies actually the point, the center of the rotation. So around which point are you actually rotating the image? So if I specify this, I'm basically saying that you rotate the image at around 128, basically the central point of the image. Okay. And I'm specifying the angle of the image as well. I mean, through how many degrees should it be rotated, basically in the counterclockwise direction. And the 1 specifies that whether I am trying to magnify the image or not. If basically 1 means that I'm not magnifying the image. The output image has the same size as the image or as the original image, except that it is just being rotated through 60 degrees around the central point. So you could experiment with with different values. You could just if you just change these values, you would see that now the center of rotation, I mean the point across which the rotation is taking place, has changed. So the image has also shifted. And you could always try with just if you magnify the image. So now you see that not only has it shifted, but it has also been blown up. So these are options which you could play around with. Obviously, these would depend upon the problem at hand, which you're trying to address, the task. Okay, so these are some very basic transformation operations which you could use. So the example which comes to mind is again data augmentation, and I guess you would be able to find interesting examples if you explore the related literature. So finally, we come to the image filtering part, which is basically look into the smoothing operations or the blurring operations. So here for the sake of demonstration, we are considering the Gaussian blur or the Gaussian blur function, whichever way you want to say it. This is basically used. Gaussian blur actually finds uses when you are trying to extract. Yeah, does anyone want to speak? Okay, so as I was saying, so the Gaussian blur function comes very handy when you're trying to extract features such as edges, like edges of objects or edges of faces. So here you can see in the output you have edge detection is very it's a very good application of Gaussian blur function, and it is also less susceptible to the image noise. So what happens is the edge detection might be thrown off by the grains in the image or other visual artifacts. So by smoothing the image, you actually get rid of those things, and the higher level features such as edges and shapes, certain shapes, those things become more prominent, and the learning becomes a little easier. It does lead to a loss of information, but we are just trying to extract the higher order features. So so the Gaussian blur is implemented in OpenCV by using this Gaussian blur function, where you feed in the image. And if you are aware of the actual mechanism of Gaussian blur, it basically uses a Gaussian kernel. So a Gaussian kernel is basically a square matrix, if you can call it that, a square matrix whose dimensions are taken as odd. So why is it taken as odd? So it will be either 3, 3 or 5, 5, or maybe some other bigger odd number than that. And that is because you need that central pixel. So if you can imagine Gaussian kernel, let me just show you some images here. If I can just give you an idea. So if you just look at this image, this is a very simple image of a Gaussian blur kernel. Yeah, so this is what you would get if you have a 3x3 Gaussian blur kernel. And just like a Gaussian distribution, where the central if you know that there is a peak at 0, the central measure, and it's sort of slides off, it falls off at both ends, it tails off at both ends. We are all familiar with the bell-shaped curve of the normal distribution. Just like that, the weightage towards the center, the weightage of the central pixel of the Gaussian kernel is the greatest, and it falls off as we move away from this as we move away from the central pixel. And that is used to actually compute the filtered values, or the I guess we could say filtered values of the output image. So how you do it is, if you just go back to this image, you place this kernel. If you want to find a value of a filtered value of a given pixel, you just place the kernel on the image such that the central pixel is overlaid on that pixel. Okay, the central pixel of the kernel is overlaid on that pixel for which you want to find the filtered value, and then you compute the weighted average of all the pixels which the kernel covers. So you basically multiply 1 with whatever pixel value is underneath that, 2 plus 2 with whatever pixel value is underneath that, and you compute the weighted average of all those pixels, and you plug in the weighted average value to that pixel for which you wanted to find out the filtered value. So that is how the operation works. That if you should just consider the very basics of the Gaussian blur operation. So this operation is basically what we refer to as a convolution operation. So convolution operations you will come across later in the machine learning, in the machine learning courses where you look at convolution neural networks. Again, there will be uses of kernels, different types of kernels. So, but here we are using a Gaussian kernel to blur the image. Now, depending on the, if you are aware of the Gaussian function parameters, depending on the value of the standard deviation, the sigma, although I do not have it written here, the sigma actually determines the how sharp is the peak, or rather how much of a weight the central pixel of the kernel would have, and how steeply, or rather how smoothly it would fall off to either side. So depending on that, you could actually have different types of blurring. So if you see, I have specified 0. So by default, the input to the sigma parameter is taken as 0 for the Gaussian blur, and you could always increase this parameter. You could, although I do not think it would be much visible, but what happens is, if you increase the parameter, the blurring becomes more prominent. If I can just zoom into it a little further. So with 0, you would see that it is a little bit clearer. But if I can just increase it a little more, see, if I do not know how much clarity the transmitted image will be, but the blurring has actually increased. So what happens is, if you increase the sigma parameter, the standard deviation, you actually flatten the peak, and by doing that, you actually just sort of reduce the weightage of the relative weightage of the central pixel with relative to the surrounding pixels. And what that does is it actually increases the blurring, and the edges become more blurred, and it is not very. It leads to a more the loss of information is more in that case. So again, this would again depend on the specifics of the problem which you're trying to solve, and again, it is all dependent on what you're trying to finally do. So that would actually determine what parameter values you are setting, whether it's a 5x5 or a 3x3 kernel with whatever standard deviation parameter you're setting.
So can we also increase the sharpness of the image if we can blur it?
Yeah, so that is what I am coming to here. Okay, so I have not really dealt with the sharpness explicitly, but there is something similar which we can do, which is basically the equalizing operation. So if we go back to the original, the single channel histogram, we will see that there are regions where the pixel intensity count is not that great. These values do not have lot number of counts. So in order to sort of boost those values, in order to increase the counts of those values, in order to boost the sort of, you could say loosely, to boost the brightness or the contrast of the image, which we have labeled it as contrast enhancement. To enhance the contrast, we could run an equalize hist function. Basically, it brings up those low areas in the histogram to the higher areas. So it basically just equalizes it. Just you get something like this. They have just bumped up the curve. So equalize hist is basically giving you the same histogram with the values sort of like boosted up, and you could store the the modified histogram. So basically, by running this function equalize hist, you are storing the modified histogram in EQU. You could just adjust a variable, and then you are storing the EQU as a yeah. Oh, I beg your pardon. Just give me a moment. Okay, so I'm just I just said something wrong. So basically, what you're getting is, by doing this, you're basically getting the image that would result from running that equalize operation. And if we can then store it as a this is where the image write function can come handy. We need to store the modified image, and then you could plot it as a separate image, and you can see that is what it has done. It has basically the images, the parts of the image which were already a little bit lowly exposed. It has sort of enriched the black areas of the image, and consequently it has also brought up the brightness of the brighter parts of the image as well. So you can see this in comparison looks more flat compared to this. So here the bright parts have almost like been overexposed, and the darker parts have been sort of been crushed, giving it a more the contrast has been greatly enhanced in this case. So that is how you can do it, by just equalizing the histogram. And yeah, so those are some of the basics of image processing which you could carry out in Python. And
sir,
yeah, please.
Sir, means after the enhancing, then in the graph you showed, why is everything red? Like
no. Once again, please do not be confused by this red. If you are asking about the color, it is just a it's just a color we have chosen to just plot the graph. It's just a color.
No, sir, not about the color. Like before there was a normal graph, but this time the graph has thickened. So
yes, so that is what I was saying, right? Because in the original histogram, you would see that the counts for these pixel values are very low. Okay, so just as an extreme example, you could see that these areas, so these pixel values represent two very dark areas, and you can see that the counts for such dark pixel values are really low here. But if you now switch over to the equalized histogram, you could see that these leftmost regions, they have also been shot up, they have also been increased. So what it has done, it has basically brought everything to the highest possible level. So by doing this, you are increasing the counts of these pixels, the pixel values, and what that has resulted in is that the darker areas have been made more dark. If you just consider it in just plain terms, the darker images have been made darker, even more dark, and even the brighter images, which are already the well exposed parts of the image, which were already exposed, which were already bright, their brightness have been further intensified. So what it does is it is the basic contrast enhancement operation. It is what we do in basic image processing programs like image editor or Photoshop or whatever be the case. So we are basically crushing the dark areas, crushing the dark, like enriching the darkness of the darker areas further, and bringing up the brightness of the brighter areas even more. So it is just blowing up the extremes even further. That is why you are getting this enhanced this contrasty look to the image, and that is a result of this equalization operation, that all the counts for the pixel intensity, pixel values have been shot up, have been boosted up by like so. So that is why you're seeing that what I said, the contrast has been increased.
Sir, actually, I understood that, but like for each pixel, there will be a single value, right, which is increased to a single value. So why all of the region, means if we consider along the y-axis, let's say at 50, along x-axis at 50, the y-axis, there is a straight line like that. So why is it like that?
No. See, the thing is, you have to understand that the x-axis actually represents pixel intensity values. Okay, so these are not like individual pixels. These basically what the histogram tells you is that how many pixels are there in the image which have a pixel value equal to something, equal to say 250 or equal to 120 or whatever. If you are considering 0 to 256, how many pixels are there which have a value equal to a certain intensity value? So that is what is being shown in all of the histogram images. So here in the original histogram, if we go back to the first plot, that is what it is being being shown in this plot, that pixel which have very low values. So here you might have a pixel which has a value, say 10, and the count of the number of pixels in the image which have a count equal, which have a brightness equal to 10, that is very low. But in the equalized image, the count of pixels having that value equal to 10 has been increased, have been brought to the same level as counts of pixels having values, say close to 250. So that is what I am saying, that the images which were, the parts of the image which were dark are now even more darker, even more dark, and parts of the images which were bright are again, I mean they are bright in compared to the the darker areas, and they have been also boosted in relative to the darker areas. So that is what is happening. The counts have been modified. These are not individual pixels, rather individual pixel values. And the histogram is telling us how many pixels are there in an image which have a particular pixel value, pixel brightness value. That is what is.
So there is a threshold value, and then below that, if it's dark, it'll just push it to the darkest value. Is that how it works, or?
I am not sure about the internal workings of the equalized histogram. So that is another thing. I will get back to you with the internals. You could always look into the OpenCV documentations, but yeah, I confess that at this moment I am not versed with the exact details of the function, but the overview is that it just brings everything to the same level. It just brings the pixel value counts to the same level.
Sir, shouldn't it be a straight line if all the frequencies are nearly same?
No. See, that's the straight line is what you get when you are talking about the just the values. But these are peaks, right? These are like counts. So you are not being able to see the individual peaks, the individual plots here. But I mean, it has all been squeezed into. Could someone just mute his or her microphone? There's this background noise coming. Yeah. So you're just squeezing the entire peak like this, and since you have shortage of space, and that is why you are seeing this this red mass, this compressed graph. It is just all those peaks have been brought to the same level, and it has been just squeezed into this this plot area. That is just a feature of the display of the plot. So, yeah, so that is basically where this brief tutorial comes to an end, and you could always build upon those things which we just saw. And there were a few things to I will address either on the general channel, or I will get back to you via mail or some chat oriented options. So if you have any further doubts, do let me know in the Teams channel. And yeah, that concludes the tutorial on the image processing part.
Sir, you'll be sharing this one, right? This notebook.
Yes, I will of course share the notebooks and the the image files for you to work around with. Okay. So I'll just end this. I'll just stop the presentation.
Sir, can I group?
Yes, someone was asking something about a group.
Sir, can a group have 7 members?
See, it was discussed that around 5 to 6 members are allowed. Now, you would have to consult with the course instructors regarding the actual number, because we cannot really make any concrete comments on this. It is better if we stick to 5 to 6 members, but any further changes, I think it is better to consult the course instructors, either Professor Paik or Professor Mitro on this, or the Professor Jigmohan. So,
also, sir, regarding the tutorial, like, would it be posted on Teams or would it be available in Moodle?
We will create a folder. So I guess this has been a system carried out for the past few semesters. We will create a folder. Are any of the other TAs present? Has there been a folder made on the files section? I guess there is a folder now, right?
Yes, Amudinta, so we will be providing all the files in MS Teams itself, like students can find them. And now I think you can take some questions from students regarding your presentation. Then Priyanka will continue. I think we don't have much time.
Okay. So I guess I have pretty much addressed the questions to my part. I think I can now shift. I mean, hand it over to Priyanka because that part is still pending. So students, any further questions? You can contact me on the Teams channel, and now I just hand it over to Priyanka.
Is my screen visible now?
Yes, Priyanka, your screen is now visible. No. You are audible. Make sure that you're presenting your screen.
Okay.
Yeah. Now we can see your screen.
Thank you. New file. So first of all, we will be creating our new file. I will be writing in the file using f.write syntax. Parentheses, and finally to read that we can
Hello.
Priyanka, your voice is breaking. Make sure that you're having good internet connection. Maybe it's because of internet connection. We are losing your voice. It's breaking.
Is it fine now?
Yeah, now we can hear you, but in between it is breaking. Continue. Carry on with the presentation.
Okay. Us 7 words, so we can write this as that, like f.
If you're using a Bluetooth device, you can disconnect. Like it has some latency, so. Use a wired earphone or something.
Is it fine now?
Yeah, now we can hear you, but in between the voice is breaking. Maybe it's because of the Bluetooth device. Try disconnecting the Bluetooth device and use normal earphones, wired earphones.
Yeah. It's disconnected on.
Okay. Now carry on.
Wired earphone. So from this, our cursor. So if we again do this, we will go to the next 7 words.
Ma'am, again we can't hear you.
So
So Priyanka, in the chart section, one student has suggested like you can present your screen from your laptop, but you can use your mobile phone for audio. Like you can connect your mobile phone to audio device and you can speak. You can present your screen from laptop. I think it works. Can you please try it once?
Yeah, sure, I will. Try that. Am I audible now?
Yes, you are audible. But make sure that switch.
Yeah.
Switch off the laptop microphone.
Yeah, I have done that. Okay.
Now carry on.
Okay, so to get the sixth position, we can just use seek as a in the instruction. So that's how it will get to the sixth. And again, if we do f.read, it will start reading from the sixth word in the sentence. So this is like 1, 2, 3, 4, 5.
Are you sharing your screen?
Are you sharing the notebook?
I think you're not sharing your screen. Share it on laptop.
I am sharing. Okay. I will again reshare my screen.
Yeah. Also start from beginning. Some students have requested they cannot hear anything from beginning. So try to explain from beginning.
Okay. So W is for create a file or overwrite if that's already exist. F.write will write all the content which we want to fill in that file. Close to just close that operation, and then again R. Are you getting it?
No.
We cannot see.
Steam got stuck. It is.
Now it is visible. There is some latency. So now you can start from beginning and start explaining now. It will work now.
Okay. So again, to open a file, we just write open parenthesis file name and the mode. So if you write W stands for overwrite the file if it's already present, or else it will create that file. Write stands for write all the contents which we want to fill in that, and slash and it's for the next line, and that R, because this is the same syntax but we are changing the mode. So R stands to read the file. So now we can read the file whichever we have written in the previous cell. So this is that, and again it will read all the contents in the file. So if we want to read first 7 words,
can you explain it from the starting?
It's the starting. What you wanna ask, you can ask me.
No, just now the screen was visible. Like just now came.
Okay, fine. I will start. So it's like its syntax is like file name, whichever variable we want to use, then open if you want to start a new file or overwrite a file, and then the file name, and then the mode. There are various modes which I will be discussing later. So this W mode stands for overwriting a file if it's already present, or else it will create a new file. F.write what it will do, it will write all the contents in that file, and after doing all this we simply use close operation, and so that we can switch on over to other operations. Now if we want to open the file in the read mode so that contents will not be changed, so we can simply use f.read empty parenthesis. It will read all the content in that file, and if we fill some numeric value, it like 7, it will read first 7 words in that first 7 alphabets in that file, including space as well. So, and from that cursor, yeah.
They're like only in a single line the whole message got printed, right? Like that slash and did not work. The next line.
Yeah, it will be like that only. So for the this thing f dot read parenthesis, our cursor position will also change. So again, if we do the same thing, we will start from the next 7 words. So, and if we want to know where our cursor is actually right now, so we can just use f dot tell. And if you want to change our cursor position to say 6, we can simply use f dot 6. And again, to check that like whether it's working or not, we can simply use f dot read parenthesis. So you can see this was our original content. So after using this, our this output is starting from the S. So this means our cursor position is changed. So like this is another thing, like f dot 60. It means cursor will be at 0th position, and it will print all the lines present in that file. So if we do that, see, now you were someone is asking about the slash n. So by doing this looping thing, we can print it in the different lines. So now other thing like f dot read line, it will just read single line, that is the first line present in that file. So to read another line, we can again use this because our cursor position will be changed. So it will read the next file. So again, to that get back to the first, get the cursor to the first position, we can use this f dot read lines. It will read all the remaining line from that cursor position. So if we want to add some content, meanwhile, we can use a plus mode. So like I have written the file has been rewritten. So this will be added in our file. So this is the same thing. I added the 4th line in that file. So OS stands for operating system command. It's a library available in Python. We can use it to remain our file. So that's how you can see. So file name is changed, sample.txt, as you can see. So you can simply remove that. So first of all, we will read first line from that file, and then we can simply remove it from that. So it's removed. So now comes to the next topics. Anybody having doubt till now?
Screen is stuck.
Okay.
Priyanka, can you please upload the file in MS Teams now itself, so that students can, they can view from their desktop itself, even if you have internet issues. So upload the file in MS Teams file session, lab material.
Yeah, sure, I will do that.
Yeah. So students, tomorrow I think Joel sir will be giving an assignment for you all. He will be giving the deadline, and he will announce like after making the teams, he will give enough time for submitting. You have to submit on Moodle. You have to use Python, and you don't have to. Sir will explain like what exactly has to be done in that assignment in the document. which we will be uploading in MS Teams probably tomorrow or day after tomorrow. So after formation of teams, we will give you enough time for that assignment.
Just a moment. Yeah, it's uploaded now. You can check. Hello?
Yeah, okay, Priyanka, you can share your screen again and can start presenting. They will
Yeah.
simultaneously view it from their screen.
Okay. Yeah. So now we will move to the next topic, plots. So is it visible now?
Yes, it is visible. You can continue. Yeah, it is visible. You can continue.
Okay, thank you. So this plot section, I will be first loading all the library packages I will be need. So NumPy for all the mathematical operation, pandas for the data set or data frame, and matplotlib is a library which we basically use for plotting purpose. It is built over NumPy, and other libraries like Plotly, scikit-learn, etc. are built over this library only, and we will be using Seaborn for some of the plots. So first of all, bar plot. The bar chart or bar plot is useful for categorical data for having category less than 30. Above that number of category, it will be messy. So you will not be able to understand anything. So I will be creating a fake data set like height, this, as you can see in the list, and the name of bars, like which I will be using as labels A, B, C, D, E. And if this plot.bar, PLT stands for matplotlib.pyplot. And pyplot is a sub package that is present in the library matplotlib. And like these bars will be like x-axis or y-axis things. Oh, just a minute. So this bars, like these bars, you can see in on the x-axis A, B, C, D, E, and the height you can see on the y-axis. Correspondingly, bars will be plotted, and plot.show, in every plot it will be like plot.show if you want to see that plot, or it will be plot.grid. If I will be using plot.grid somewhere, in that it will be in grid form. Let me check here. See, you can see this plot in the grids form. I think there is some lag. Yeah, you can see now, I think. So this is the thing with the normal bar plots. If we want to do, there are two types of bar plot, horizontal and vertical. Some of the time what happens, like you have labels over axis which are having large names. So you will prefer bar plot, horizontal bar plot for that, so that it will be readable. So like horizontal bar plot, it will just use BAR, H stand for horizontal plots, and other things are quite same. So like these bars will occur on the y-axis and rest will be the same. So if you will run that, you can see it's just a 90-degree version of that normal plots. So like coming to the various adjusting with that, like colors, you can change with, play with colors, line colors, edge colors, etc. So you can simply add colors, and if 0 to 1, transparency is used. Accordingly, you can see the different colors. Similarly, the next cell you can see. If you have any doubt, you can ask me in between. And similarly, the parameter, you can see its parameter and you can use
Ma'am, what
H
does
color.
X and Y ticks do?
X ticks. Okay, it's like the bar thing where you want to say that you want to see that x-axis or y-axis. If you want to see at x-axis, you will simply use x ticks. If you want to see at y-axis, you can use y ticks. Is it clear?
Ma'am, without it, it is also running fine.
Yeah. The default mode will occur over that. If you want to change something with that, you can use it. It's just an extra thing if you want. So coming to like adding title labels over that plots. So for adding title, we can use plot.title, title name, and the font size. And adding label for the x-axis, we can use plot.xlabel, what name you want to keep there, and the font size. And font size is that like you may leave it because there is always a default value set for that. And similarly for the y label. And again, if you want to set the values for the y-axis or x-axis, you can simply use y-lim and the values which you want to keep there. And you can simply run that. So it's like, I hope you can see that. And like it's simply a latex version for the title. So bar plot is complete. Now we'll come to line chart. If you guys have any doubt, you can ask me. For the light.
For the color part, can you explain once again?
Color part. So you can like if there are like 5 bars in our bar plot, you can add color in the list form. Like you can see in the cell number 22, I think 22 or 24. That color is equal to black, red, green. So you can change it, and if you want to like simply one color like B, R, G will also work for some of the colors, or else the hexadecimal code will also work. I will show you that later in this notebook only. Is it fine, or you want to ask something else?
Yes, ma'am. Yes, ma'am. Fine.
So now we'll come to the line chart. Line chart, I will be creating a data set for that. Like PD stands for pandas. Data frame is just a object we used over there. Like they are using years 2015 to 2019, and it's just a cricket data set, T20 and ODI values. I simply filled it there, and you can just simply use the plt.plot. Year will be on the x-axis, T20 will be on the y-axis, but name like from where data you're picking. DF, we have already given that name in the previous line. If you will run that, you will get this plot, if you guys can see. Okay, and now again, if you want to customize like using titles, labels, and legend, you want to name it, so you can simply use it. See, so coming to the, like I have plotted 2 plots in the same area, and I have used different colors for that. So x dot ticks, like I told you where you want to see that. It simply like giving a range, what value you want to keep there, and the font size what you want to keep there, etc. on the x-axis. Similarly for the y-axis, because that's just a numerical value which I'm using here. So that's why I can use that here. And the title, which title you want to give, X label. Similarly, as I have already explained, X label like years, Y label like points, and legend like what you want to, where you want to place it. The location stands for the upper center, like you can keep it right, bottom, etc. You can keep there is some other variables also, you can change it later on. Other will be like default value. Okay, and that's how it works. Line well. Okay, now another is not. I want to show you how the hexadecimal color values actually work. So I can take some, just a moment. Actually, I have just displayed the Excel. You can simply keep the color in hexadecimal code as well, but the thing only is you have to define it as a separate variable in ax.plot, and this you will be asking like this is a different way of plotting things like plt.subplots. There are several applications I will show you later on. So fig.ax. These are two outputs which will be fit to these variables ax.plot. So like fig, yeah, you can simply use it to save the figures. I think I displayed it. So the one thing I want to show you is this only color thing, like how you can use a hexadecimal code of color. So coming to the multiple line charts, like how you can represent multiple line charts in the single plot only. So this is the thing. So there is an interesting thing that's coming over, like markers, like how you want to see that particular line. Like you can see X, Y1, I am using marker O. So you can simply, the below blue version of that line. So O will be simply representing as a dot, and marker face color blue, and marker size and color like sky blue, which you can already see. Similarly for other like markers, you can see, I think. And similarly for the line style, there are different line style, like solid line, you can simply use a hyphen for that, and dashed line, you can write it like that as well. Okay, yeah. But if you want to see several plots side by side, so you will use plt.subplots, like 1, 3, like 1 row, 3 columns, and where you want to see particular plot, you will place that number. Like I want to see this plot over the first place, so I am keeping it 1. Like y label, what you want to plot on the x-axis is x, then y1, and similarly other things are same. And CRO01 is just a collective, like R for red, O for marker style, and this hyphen for line style. You can see this is a solid line. Similarly, for all the other plots, you just keep changing the third value in plt.subplot. So it's clear now. Okay, similarly for the next cell, you can see. Yeah.
Excellent ones. Yes. Left. Hello.
Yes. What are you
Explain it
saying?
once again. Explain it once
Oh.
again.
What you want to this PLT dot subplot, or is this something else you are asking?
The subplot equal 1, 3, 2. That's one.
Okay. So 1 stands for the number of rows, 3 stands for number of columns, and the next variable, number stands for where you want to actually keep that particular plot. So this x, y1 versus x, I'm keeping at the first position, and you can see y2 versus x, I'm keeping at the second position, and y3 versus x, I'm keeping at third position. Is it clear now?
Okay.
Okay, and here you can see there is some overlapping over the plots, like y2 is overlapping over the plot of y1 versus x. So to avoid that, we can simply use fig dot tight underscore layout. So what will happen? The overlapping will be removed. So to simply save that figure, you can simply use fig dot save figure, and what name you want to keep and what resolution dots per inch you want to keep there. So it will be saved here. I think again some error is over there my laptop, but you can simply save that file over your desktop like that. So I have completed the line plot. If anyone have any doubt, they can ask me. Okay, I'm coming on the scatter plot. So how you can use it? Like if you want to identify relationship between two variables, you want to see the correlation over that, you can use scatter plot. So the thing is, like, it is just for simple plot you are using plot plot, and for bar plot you were using plt dot bar. Similarly, for the scatter plot you are simply using scatter, SCATTER, else things are same only. So you can see, like, how I'm just creating a scatter plot for x and y1, if you can see. So that's how. And similarly, you can create a scatter plot for multiple variables. Like I'm creating a rough data set like x, y actual, and y predicted. So if you see that I'm giving different color for y actual, like pink color, and for the y predicted I'm using yellow color. So this is how you can merge our two plots, scatter plots. So now coming over to the histogram, which we normally use for data analysis. So the thing is, like, everything is like almost same. You are just using plt dot hist, then what you want to see on the like x-axis and y-axis beans, like how many beans you want to see, 0, 1, 2, 3, 4, 5. So as you can see, y fret has multiple random values, but whichever values are like lying between 0 and 1 and 1 and 2, 3 and 4 are coming bit, and this r width, this is called relative width. It will be like whichever value you want to keep. I'm keeping 0.9, so this width will be set over there. So the other thing is like box plot. Box plot is like a very simple plot which you can use to describe your data set. Describe, I mean to say, by describing, like, you can get all the summary in this box plot. Like you can see the medium, first quartile, and third quartile, and the maximum and minimum value. So this is how it will look. So this, if you can see the middle yellow line, this is our median value, and extremes of that this box is like our like lower value will be the first quartile and upper value will be the third quartile. And you can see two whiskers are there, like lower whiskers represent the minimum value, the extreme represent the minimum value, and upper whisker extreme is representing the maximum value. So this is how it will work. And there is some violent plot as well. It is just like it is very only used when you want to see the data distribution with this thing. So in between you can see the box plot thing, and over there side you can see the distribution that is present over there. And for this I will be using this Seaborn library, where is this package is already present, violent plot. And there's a box plot you can also fetch from this Seaborn library. So this is it. So there is some KD plot as well, like for the probability density function if you want to see. So this is also from that Seaborn library. So this plotting thing is over. If anybody have any doubt, they can ask me. So I will be coming over to the data set part. So there are few data sets which are already available in the libraries. Like you can see the Amnist data set, you can see the fashion data set, ImageNet data set that is already available in our libraries. Like sklearn have IRIS data set. If you will load that, you just need to do some little, let me, see, you can see the values that are present in this data set, but you need to do some changes over there. So for now, I'm just using a CSV file, comma separated file, which I have downloaded from online. So this for reading this, I'm using pandas library, and read underscore CSV. It will read our CSV file. If you want to check its shape, so it is 150 cross 6, 150 number of rows and 6 number of columns. If you want to see the first 5 values present in that data set, you can simply use dataset.head. And similarly, if you want to see last 5 rows present over that data set, you can simply use dataset.tail. So this is how it works. See, just now we got to know about box plot. The box plot is just describing this dataset.describe in the plot form. So what it is saying, like, but like there are different values present in our data set. So it will be just give his analysis in the form of mean, standard variation, standard deviation, and mean, 25 percentile, 50%, like first percentile, second, something like that only, maximum minimum value in just a concise form. So like there are 3 spaces, if you can see over there, like Setosa, Virginica, that are present in our data set. So if you want to know like how many values are for each class present in our data set, you can simply use like dataset dot group by, which you want to, like class, you want to place the class name. So like see, this is species, there are 3 species, so you just name this label in that place, like dataset dot group by. If you want to count the number of genre present in particular movie dataset, so what you will do, you will just use dataset dot group by this quotes and this genre and dot size. So it will just give all the descriptions there only. And similarly, you can just remove, like this is just another way of doing the same thing. Okay, so I will be just using that plot thing over this data set. So like pie chart is another thing which we use for our data analysis. So it will like you may be knowing that this total values are 100. You will just identify the portion of different component present there. So this is how it will work. You can see all the portion are having same area, because you can see that Setosa are having 50 classes, but versicolor is also having 50 classes. That's why it is using the same area. So again, I'm just plotting that data set. See, these different colors are provided for each attribute for our data set. And similarly, you can plot that histogram as well. So it will use one of the attributes, and like one of the value will be like this ID thing only. Any doubt till now? Okay. So similarly, we can plot the scatter matrix for our data set to see the correlation over the different attribute. Because some of the time what happens that for our machine learning algorithm, there are so many attributes. So we have to check what do you want to use for your algorithms. For that thing, you will need to analyze your data. For this purpose, you can use different plots for that. Similarly, this is just another way to generate some synthetic data set, because this thing you will be asked to do for your assignments as well. So this is just a way like how you want to plot distributions. It's like very rarely used, but I just wanted to show you how it works. That's why I kept it there. So like it's first of all the Bernoulli distribution, which you have already read in your machine learning thing. And this is like everything is same. Like for probabilities, you are just creating your data set sites, like because Bernoulli is using only 0 and 1 as a support thing. And like I'm plotting a bar plot. That's why I'm using plot plt.bar title x label already I have explained. So this is the same thing. And similarly for uniform distribution, you can take example of rolling your die. So probabilities, you know, like there are 6 faces, so 1 by 6, something like that only, and you can simply use it. Similarly for binomial distribution, if you are tossing your coin a number of times, you can use it. It's just using our Seaborn library only. So sorry, SciPy library only. This is how it works. And similarly for Gaussian plots, Poisson plots, like you may be knowing, like it is a like it is a discrete probability distribution function. So it's it has its own use. And then finally the exponential distribution, it is using lambda variable that is equal to n over p, and it's used when n values are so large and p values not small. That's yeah. Yeah.
अरे कुछ करा नहीं रहे तब से वो लेक्चर ही दिए जा रही है कि ऐसा ये करना था ऐसा वो करना था जुपिटर नोटबुक।
Sorry. So I have finished it. So if you have any doubt, you can ask me. Is there any doubt?
Please tell assignment model questions.
Sir will probably send that because I don't
I am
have
not
it.
telling about the. I am asking about the assignment questions model, not what are the questions. Means.
You can search that online because sir was saying that he will post that later on.
I'm asking models, ma'am, not you. I'm asking the sir.
Like he's asking what type of questions would come in the assignment, not the exact question.
Simply like whatever we have taught, based over that only, it will not be anything different. You can simply check online.
We don't know how to train data.
It will be based on the basics only, because right now I don't know much about that, so I can't tell you.
Where is the sir? Okay, not you. Where is the sir? Right? I want to ask sir, not you.
Sorry.
Listen.
Listen. I want.
Who is this? Who is speaking now?
My name is Samir, sir.
Yes. So see, the course instructors are not available for this session right now. But he has informed us that the first assignment will be posted tomorrow, and you will get to know of the details tomorrow itself. So no need to get worked up about the details of the assignment right at this point. As soon as you get the assignment tomorrow, go through it. If you have any doubt, post it on the channel. You can place a query to the TA, to us, even the course instructors. But it is better to route the queries about the assignments through us. We'll get back to you.
Okay, sir.
So we'll be stopping mid.
I think we can conclude the session for today.
Okay.